We had already discussed about geostationary satellites in the previous video. Now in this video we are going to start with the height and orbital velocity calculation for geostationary satellites. Now the starting procedure or the starting lines that you get will be similar to that we have found to describe the artificial satellites. That is mv square by r is equal to gmm by r square, where r is the orbital radius of the satellite from the center of the earth, v is the velocity orbital, m is the mass of the earth, and small m is the mass of the satellite. From this we have derived that v square is equal to gm by r. Replacing gm with gr square, we have found out the velocity v is equal to square root of gr square by r. Now t, or time period of a revolution, this is the time period of revolution. So t is equal to starting was 2 pi r by v, we had get 2 pi r by square root of r by gr square is equal to 2 pi root over r cube by gr square. So the expressions are similar to what we have found out. Now from this expression, if we square both the sides, t and this one, so t square is equal to 4 pi square r cube by gr square. And from this we are trying to find out the value of r, small r, that is the distance of the satellite from the center of the earth. That is r cube is equal to gr square into t square, gr square into t square by 4 pi r square, the denominator as denominator. Now value of r is equal to, so gr square t square by 4 pi square to the power 1 by 3. Now replacing the value, that means we are trying to find out the radius of orbit of the geostationary satellite from the center of the earth. Time and again I am repeating a single phrase, from the center of the earth. Calculation distance of the satellite from the center of the earth, that is r. Now if we replace the t, or the value of time period of revolution, we know it is to be 24 hours. That means 24 into 60 into 60 seconds. Again we know the value of pi, we know the value of r also. R is 6400 kilometers. That means we have to replace it by 6400 into 10 to the power 3 meters. Value of small g as 9.88 meters per second square. Now after replacing these values, we get, or we calculate it with the help of a calculator or something. That means 4.234 into 10 to the power 7 meters. You can calculate it yourself. Now converting this to kilometers, we can get 4.234, that is meter. So 3 subtracted, that means 4 kilometers. 1000 meters make 1 kilometer. Now approximately we can get 42340 kilometers. I can write it approx. You can use the sign also or write approx. Now this is the distance of the satellite from the center of the earth. Now what is the distance of the satellite from the surface of the earth? The distance of geostationary satellite from surface of earth. So we have to subtract the radius from this, that is, we know that is 6400 kilometers. Now this comes out to be somewhat 35940 kilometers. So approximately we can take it to be 36,000 kilometers. So this is the approx value for the distance or the height of the satellite from the surface of the earth. And the velocity, that is v is equal to 2 pi r by t, 2 pi into what was r, that means the distance of the satellite from the center of the earth, that is 4.234 10 to the power 7 meters by t. T means 24 into 60 into 60. Now from that we can calculate 3079 meters per second. and converting this to kilometer per second, 3.079 kilometers per second. So this is the value of orbital speed of the geostationary satellite, and this is the distance of the geostationary satellite from the surface of the Earth. Now a very few points to discuss about geostationary satellites. One is, if we can start with the uses of geostationary satellites. Where are geostationary satellites used? Nowadays, geostationary satellites are in extensive use for weather observations. The first we can say that is weather observations. Second one is TV. Third one is radio broadcasting. This is a very old thing, not new to you people. 4, we can write telecommunication, etc. Now few more things, that is the games and entertainment programs performed anywhere in the world can be transmitted and telecast live. The live telecast that you see on the television, they can be telecast live at other places using these parking satellites on a geostationary orbit. Now geostationary orbit, as this moves along the geostationary orbit, or this is the equator, this moves along the geostationary orbit, so it covers a large part of the Earth's surface, maximum that can be done by a satellite. So again I repeat that cricket matches and all live programs that happen in the world can be telecasted live to other places using this parking satellite or geostationary satellite. Now, difficulty in use of geostationary satellite. That means this was the last thing that I had discussed, is live telecast. Now what happens when we try to telecast a live program is that the signal. Now suppose this is the Earth, a live match is going here. Now this telecast has to travel 36,000 kilometers to reach the satellite, and then has to come down another 36,000 kilometers to reach the point where we are seeing the live telecast. So total distance of 72,000 kilometers. A distance of 72,000 kilometers has to be traveled by the signal. That means a minimum distance. This is known as the minimum distance of travel before a signal can reach you. Now this distance coverage will require a time delay. Of 1 by 4 seconds. 1 by 4 seconds. This is the time delay. That means when the event is occurring here, you are watching that event after a time lag of 1 by 4 seconds, known as the time delay. Now this is very negligible in the case of radio or TV broadcasting, but it causes inconvenience in telephonic conversation. This is the time delay. You cannot understand, you cannot view the real match and the view that you are observing at the same time. But whenever you can get a radio telecasting a cricket match, you will find that both the television and the radio are switched on at the same time. You will find when a ball is bowled, as described in the radio, you will see that ball bowled in the television after a slight amount of time. Little bit of time lag is there. But this causes a great inconvenience in telephonic conversation between two countries, because due to this high orbit, the spatial resolution of data is not as great. So after this, humans or the scientists have discovered another type of satellite known as the polar satellite to reduce this spatial resolution of to increase the spatial resolution of this data, because that was not great for the geostationary satellite. Those satellites are known as polar satellites. We are going to discuss that after this. Now the second difficulty, this was the first difficulty. The second difficulty is that the plane of orbit, as I have drawn it, the plane of orbit of the geostationary satellite, here I have drawn it. The plane of orbits of geostationary satellite coincides with the Earth's equatorial plane. Now, hence they cannot function properly for the zones closer to the poles. This satellite will not function properly for regions close to the poles. Here, they will not function properly. This is the second type of inconvenience that one has to face while using the geostationary satellites. Now, you can write this as not proper functioning at poles. Now, polar satellites. Now, the two hindrances that we are facing with the use of the geostationary satellite can be rectified by the use of polar satellites. Now, first we try to understand what is a polar satellite. Now, this is the Earth. The geostationary satellite plane, the plane of rotation of the geostationary satellite coincides with the equatorial plane, but the polar satellite is just the opposite. The polar satellite revolves in the polar plane. This is the polar plane from the North Pole to the South Pole. Now, first thing we have to understand that the height of these polar satellites, that means they are placed 700 to 800 kilometers above the surface of Earth, So by definition we can say the satellites that are placed 700 to 800 kilometers above the surface of the Earth and aligned with the polar plane. This is the polar plane. Aligned with the polar plane are called polar satellites. Now, using the satellites, a signal can reach from one point of the Earth, that is from one point of the Earth to the other. A signal can reach from one point on the Earth to another point in approximately 1 by 100 seconds. So the time lag here is 1 by 100 seconds, whereas the time lag here was 1 by 4 seconds, which is huge. Now, 1 by 100 second is a very, very small time. The time difference is a very, very small time. There is practically no time lag felt during telephonic communication. Now, these satellites also do away with the problem of reception and transmission of signals in the polar region. That means the second point or the second problem of using geostationary satellite was not proper functioning at the poles, which can also be taken care of by these polar satellites. Now, one more important thing is the period of revolution of these polar satellites. Now, these satellites have an approximately time period of revolution equal to approximately 2 hours. That is to revolve around the Earth once a polar satellite takes a time of 2 hours. Now, the third point is geosynchronous satellite. Now, geosynchronous satellite, in your books you will find that geostationary satellites have been mentioned as geosynchronous satellites. Now, the gross term or the total term that we can say that is geosynchronous satellite, and geostationary satellite is a particular type of geosynchronous satellite. Now, if you have to describe geostationary satellite, we can say like this. This is the Earth. This is the equatorial plane. Now, geosynchronous satellite will have a orbit like this. This is the geosynchronous plane. Now, if the orbit of a satellite is inclined with the equatorial plane and the satellite revolves around the Earth once in 24 hours, that means the time taken by it is 24 hours, similar to that we have studied in as in the case of geostationary satellite. So I have said that geostationary satellite is a special type of geosynchronous satellite in which the polar plane and the plane of rotation of the satellite becomes the same plane. Now here T is equal to 24 hours, similar to that in the geostationary case, in the direction of the diurnal motion of the Earth. Now the angular velocity of the satellite equals that of the Earth, same points as we have studied for the geostationary case. But the geosynchronous satellite has an orbit whose plane is slightly inclined with the equatorial plane. Now it is observed on the surface of the Earth, it appears that the artificial satellite is oscillating from north to south. Now this is a point of difference between the exact geostationary orbit and the geosynchronous orbit. That means for the geostationary case, we had found out that the position of the satellite remains the same to an observer on the Earth anytime he sees in the sky. But for this geosynchronous case, the artificial satellite is oscillating from north to south. That means we can write oscillating from north to south along a longitude and completes one oscillation in 24 hours along one longitude, so that it completes the oscillation in 24 hours. Such satellites are called geosynchronous satellites. Kinetic energy and potential energy of artificial satellite. mv square, I am straightforward moving into the derivation part. Gmm by r square. So v square is equal to gm by r. You can calculate this on your own. So kinetic energy, that means multiplication of half m on both sides, half m on both sides. So it becomes gmm by 2r, gmm by 2r. Now the expression for the potential energy we have already calculated it earlier, that is minus gmm by r. So the total mechanical energy or the total energy of the satellite in orbit, you can write total energy of the satellite in orbit is gmm by 2r minus gmm by r. It comes out to be minus gmm by 2r. Now due to friction, sometimes it happens that in the Earth's atmosphere or due to collision of the satellite with the meteors or the meteorites in space, the energy of a satellite, total energy of the satellite, that is minus gmm by 2r, decreases. That is, the magnitude of gmm by 2r increases. As this has got a negative sign with it, if we say that this expression decreases, that means actually gmm by 2r increases. A negative term decreasing means the positive term is increasing. Hence, the value of this small r decreases. Value of small r decreases, which means that the satellite starts shifting towards the Earth's surface. As a result, the kinetic energy, now the expression of this total energy and the kinetic energy same. Only difference is the minus sign. That means as a result, the kinetic energy, that is gmm by 2r increasing. As I have said, that the negative term is decreasing means the positive term is increasing, and the positive term matches with the kinetic energy expression gmm by 2r. That means the kinetic energy is increasing, but the total energy is decreasing. Now this is possible because a decrease in the potential energy of a satellite is twice the increase in kinetic energy, because we have got a 2 here in the denominator whereas 1 here. That means I repeat, this is possible because a decrease in the potential energy of a satellite, potential energy is decreasing, is twice the increase in the kinetic energy when it transfers from one orbit to another, because the satellite is moving towards the Earth, is coming down towards the Earth. Thus, for any artificial satellite to be working in its orbit for a long time, so for example, geostationary satellite, energy has to be supplied from outside to compensate for its loss of energy. Now, we all know the satellites have a solar panel on its backside. So, the use of solar energy for this purpose becomes indispensable, very, very necessary. Now, it should be noted that for an elliptical orbit, the expression for the total energy, that means this one, this R will be replaced by small a. I am not writing this expression here, but you can write it down in your book that this R that is used for circular orbits has to be replaced by A, that is the semi-major axis of that ellipse. Now the last topic that we are going to discuss is the weight experienced by an astronaut when spaceship is moving in orbit. When the spaceship is moving in orbit, the weight experienced by an astronaut. So small r, radius of the circular orbit of satellite from the center of the earth, as previously explained. Now g dash is the acceleration due to gravity at the position of the spaceship. That means where the spaceship position, at the position of the spaceship, the acceleration due to gravity is g dash. Now v is the instantaneous velocity of the spaceship. Capital M is the mass of spaceship and small m is the mass of the astronaut. Now R is the upward reaction of the floor of the spaceship on the astronaut. The reaction force provided by the floor of the spaceship on the astronaut. Now I have drawn two diagrams, one for the astronaut case and one for the spaceship case. Astronaut is inside this spaceship, and similar to this diagram, we will write two equations, one for the astronaut case and one for the spaceship case. So first we try to write the diagram, write the equation for the spaceship case. The mass of the spaceship was capital G. At this point the gravitational G is G dash. So it is equal to mv square by r. From this we get G dash is equal to v square by r. Now the equation for the astronaut here is mg dash. This equation is similar to that we have written for the lift case, is equal to mv square by r. Now replacing the value of g, v square by r into this one, value of g into this one, we get mv square by r minus r is equal to mv square by r, which leads us to the value that r is equal to 0, leads us to the value that r is equals to 0. That means r0 means the body weight, or the astronaut will feel himself weightless. So the